thought somebody was going to introduce me, but apparently not. So we'll just go ahead and watch my snowflakes fall while I introduce myself. So, how many people actually watch Breaking Bad just so I can understand the feel of how many people are going to get my jokes? Okay, it's a decent enough number. Good deal. So, I've got like 3 devices up here, and I'm going to try to sync with all of them because I never use my laptop for presentations. So you're going to have to forgive me as I switch back and forth between applications that I don't normally use in a presentation. But anyway, this is Breaking Bad apps. And the talk was kind of intentionally vague, if you've seen the abstract online or whatever, because I wasn't quite sure how to put forward what we were doing. So essentially what I'm going to do is talk about an application, well, a couple applications that we've designed in my organization, Capitol Hill Consultants. And I'm going to talk about how they interlink and how they actually do something beneficial for the exploit developer. So I'll start out with who am I. For those that you don't know, or for those that don't know, my name is Don Bailey, and I am from Colorado. That's about really all you care about, right? But most importantly, I've been doing exploit development for about 13 years. And I got sick of doing the same processes over and over and over. And I invented one of the first fuzzers back in like 1999. And it was the first of its kind at the time. And over the years, I've tried to augment what I've been doing over and over. And so hopefully, it's evolved into something decent that at Capitol Hill Consultants, we can use effectively for offensive security research. So Capitol Hill Consultants, just a quick blurb, we were founded about a year and a half ago. We were founded on a DARPA contract called Cyber Fast Track, which I'm sure you've heard of. We were able to analyze the entire Internet of Things scope. So we have a big focus on mobile, a big focus on Internet of Things, a big focus on embedded systems. So we like to get pretty low level, but we also do a lot of source code audits, things of that nature as well. So, first thing I'm going to do is give you a little demo, because why the hell not, right? So, we'll start out with a terrible video. And I'm kind of concerned because this screen is awful. So let's see if I can actually get this to work. The idea behind this video is that you are looking at essentially an exploit. You're looking at a Firefox exploit. Ah, there we go. Okay, sorry about that. 600. We had an issue with changing the frequency or the resolution. So basically, you're looking at a video of me pretending to browse the internet. The idea behind this is that you've got an application that we've designed called Inspector Gadget. Inspector Gadget, its entire theory is that it eases the process of exploitation. So here, I've got a website called LolDate, and this is the latest version of Firefox. And when you're browsing LolDate, the website, you're seeing profiles like you normally would. Inspector Gadget, behind the scenes, takes information from a target application that you've harvested through, say, an information leak, right? The information leak dumps memory of some kind, and the next thing you know, bam, somebody's popped a shell on your box, okay? Because Inspector Gadget is interacting with that application, reading the memory that you've leaked out of it, generating the appropriate ROP codes, and then shipping it back in a payload form to Firefox. So what you're seeing here is a replayable exploit. Like, you can probably guess what API I'm hitting just by looking at Firefox and the minimal HTML that I've got there. But essentially, that exploit is automatically working with the Inspector Gadget tool to generate an ASLR independent exploit on the fly. So it's important to understand that, because you'll have a better understanding of what I'm actually doing with the Inspector Gadget. So this tool is basically created by myself and my business partner, Matt Skinner, but it's designed as a program, like I said, that helps evolve the process of vulnerability to exploit, okay? And that's usually a pretty difficult thing. You have this simple process, right? You have a vulnerability, you need to get it to exploit. You don't know what the hell is going on in the middle. This is usually our biggest challenge in offensive research or even defensive research if you're analyzing the practicality of a particular exploit and its value against a target. You need to know if it's actually practically exploitable or if it's something that the engineers can fix at a later time, right? So exploit development, as you know, is founded on corruption. It's founded on instability. I mean, think about the terms that we use in this process, right? Memory corruption, integer overflow. These are usually undefined operations that we're abusing in order to come up with some kind of end result that benefits us as the user, right? But the whole point of that is that you start out with a volatile system. You have a volatile environment that you don't necessarily know all the effects or side effects of what you've done to that environment. So the whole process here is taking that vulnerable system, that vulnerable, chaotic environment that you've forcibly, implemented your code against, and turning it into something like a stable executional environment that's beneficial for you. So the question is, how do we get from manual labor to something automated? Because generally this process is really, really annoying. You're in the desert, you're digging holes, it's sweaty, it's hot. This is usually the problems that we have in this field, right? You want to go from that to something a little bit more simple. You want the high-grade industrial process that's very smooth and easy to clean up. And that's what we're trying to achieve here. So we have to kind of plan what we're going to do very carefully. And you saw the flow chart earlier. It was basically 3 points, right? Vulnerability, exploit, what the hell am I doing? So we're going to change that up a little bit and figure out where we're going. And this is a pretty good example. So this is kind of the process map that we came up with. And the resolution is terrible on this system. But anyway, you get the idea. You're going from the left side of the map, the vulnerable environment, and you're going through each step in the flowchart, making decisions as to what you need to do in order to jump to your payload, right? And this is the only way that you can really get to an effective, stable environment that allows you to run or inject a consistent payload and execute it reliably on a target application, okay? So these are your essential steps for a Linux, Unix platform, that kind of thing. Otherwise, this might not work in a Windows environment, but we're focused on mobile, focused on embedded, so this works really well for us. So this is a pretty specific example of a flowchart that talks about stack pivoting, because you have to take each section of the previous flowchart and break it down into itemized units, right? So this would be the stack pivoting area. And you would have just an idea of like, oh, we need to do X, do Y, do Z. We're good. We've accomplished that step. Obviously, it's not this simple. Stack pivoting is probably the hardest part of this entire process. Stack pivoting is a real pain in the ass. And it's probably the thing that I get stuck on the most, especially in environments where there just isn't a friendly architecture for it, or you've done too much to the platform, and you've screwed it up too much. Things get more complex as you get more realistic with the process of stack pivoting, but it gets increasingly complex the more that you actually attribute the different changes in volatility in the environment that you've induced based on the things that you're doing, right? And gadgets have a level or percentage, a likelihood of being volatile to the environment that you're in. So you have to reevaluate your volatility every time that you take a step in implementing a gadget. And we start to get really, really slow in analyzing these things automatically because things become too complex. And there's a point at which you have to step back and say, wait a second, this is getting nuts. We're doing too many fundamental analyses on gadgets or operations, and we're not getting enough juice out of it. So what do you do at that point, right? You have to choose one particular application, right? One particular target. You can look at as many infinite possibilities as there could be, but it's not useful. It's academic, it's interesting from an academic point of view, but it's not practical, it's not realistic. So you have to identify which vectors are going to be useful for that one operation in the particular flowchart you're talking about. So back to the whole overall flowchart process. We can basically break this down into simple steps, like I said, right? And we can learn how to automate each specific area of this flowchart as long as we don't allow complexity to drive us into a black hole, right? So we can also identify patterns at each step. So as you've probably noticed if you're doing offensive research, there's usually something that I like to call a God gadget, right? and that God gadget may be useful across an entire architecture, across a platform, or just across one particular area in this flowchart. But there's usually one or more of these gadgets that allow you to do pretty much everything that you want to do. A good example of that is just going to be like, pop RAX in return. That's probably one of the most useful pieces of code that you can find in a binary, because there are so many versatile things that you can do with that. EAX moves to a lot of registers. You're getting rid of trash off the stack. It's really easy to create operations using that particular instruction. So when you identify those particular God instructions, you have a better idea of how you can classify the use cases of every single area in the flowchart. So there are many different aspects to Inspector Gadget. I'm going to focus on 4 of them. 3 of them are based on the actual cartoon, if you've ever seen it. But one is just the ingest process. And it's to me the most important process, because the way that you deal with information when you're harvesting it is almost more important than what you actually do later when you're doing complex mathematical algorithms to analyze paths and things of that nature. That actually turns out to be really simple if you've ordered the data correctly in a database. So when you're harvesting the information, the way that you render it, the way that you store it, the way that you view it, that is all absolutely imperative towards the quality of the information that you get at a later stage. So the ingest application ends up being quite complex. We find as many ROP gadgets as we can in a target application. Okay? So we've scanned the entire thing, and you've heard about this before. Other people have done gadget hunting applications and things of that nature. But they haven't done it quite like this, because there were things that we figured out in the process of writing this that were extremely interesting. And I'll talk about some of those things. Another couple of interesting points to note are just like rebasing gadgets and vectors, but I'll talk about that stuff in a minute. What I want to get to is the initial part of just finding gadgets and where they are in memory. So I'm not going to talk too much about gadget classes, because you guys should know this, right? You've heard about it before. Gadget classes have a particular use, and they're all there. If you work on x86 architecture, you've seen this stuff all over and over and over. There are 2 things that I really want to talk about here that are important to me. So I'm just going to get down to the nitty-gritty on those. The last 2 in that list, and also another technique that I'll talk later in this presentation, return is actually really important, because on every single architecture, there's always a return n. And people never use this. I don't know why. And people don't scan for it in other applications. I'm not sure why that is. Are a lot of people actually using return n in opcode searches? Anybody? Besides me? Travis? Travis probably is. He just doesn't want to raise his hand because he's humble. But everybody should be doing this, but nobody is. On x86 architectures, the return n instruction, it just means that there's a return and then there's a value after that, okay? And I think it's 24 bits, but the idea behind it is that that value is added to the stack after the return address is popped off the stack. So you probably saw it briefly in the flowchart earlier, but there are 2 main first operations that you must take when you're developing an exploit. The first one's stack pivoting, and the second one is cleaning up the stack, which usually means you're jumping past a corrupt piece of memory or a payload or something of that nature. Return n is a God instruction that people for some reason don't ever use, because it skips over corrupted memory and allows you to continue with clean stack that you have preset up. So it's really important to note that, because I'm not sure why people aren't using it, but it's an opcode that's very useful. It's there, so please use it. And we find that as well. We also find interesting things if you're doing kernel stuff. So if you're attacking kernels, we actually look at interrupt returns and things of that nature as well. So we catalog all that information, whereas other people aren't. The other thing that I find really interesting is that people haven't done enough work with jumps. People are always talking about jump to register, right? And jump to register is important. But we were talking about that in, 1999, 2001? Jump to a register is great for gadgets, but it's not a God gadget, okay? A God gadget is going to be something that gives you an algorithm that's useful over and over and over and over for every step. And that kind of thing is arithmetic, right? So any arithmetic that you have in a function, it usually exists where? At the beginning of a function, middle of a function, or an end of a function. Everybody say middle, right? Yeah, because these types of functions, they have, the preamble, the postamble, and all that other stuff, but they have the core, the guts, the useful guts are in the middle of a function, right? But when we're using gadgets, we never go through the middle of a function. We're always looking at like the last 15 instructions, because if you look at more of that, things get too complex. They get too volatile. You're going to trash your own stack. You're going to trash registers that you've already used. So short jumps and conditional jumps are actually really useful for this, right? If we analyze memory through an entire process and identify areas in the middle of a function where we have an arithmetic instruction or sequence of instructions that are extremely useful, we can then take a conditional jump and induce the condition that we want by setting flags through a pop or some other simple gadget. Or we can just jump short to another short gadget that allows us to return to the next gadget that's interesting to us. So then you might have a mask, say you have an AND operation or a XOR operation or something of that nature. Those things are really useful, and they're very important later on in the exploit development process. A great example of that is if you're actually using mprotect, right, to change your page to executable. You need the base address of the page that you're using. And the only way that you can do that is with an AND to get the mask, to get the base page that you're then setting executable. That's actually very difficult to find, because normal gadget hunting will not allow you to find an AND instruction or a masking instruction or a set of masking instructions that will perform that operation for you. But if you start analyzing the middles of functions, then you can find that much, much easier and quicker than you ever would before. That's a very important thing. In fact, Aaron Portnoy at Nordic Security Conference was doing a talk on Windows exploitation. And he made several comments about he commonly has to jump into the middle of a function and use that function's capability to perform some kind of option and then jump to the next instruction or gadget chain, right? So that's a perfect example of somebody that's using that type of functionality already and doing it successfully. But now we can automate the process by finding short pieces of code that then result in a conditional jump or a short jump that we can abuse reliably. Okay. So that's a really important thing to talk about. The locations themselves, this is another thing that we came up with that we didn't realize was going to be as interesting as it was. Gadget locations are extremely important because they come in the weirdest places. So when we're harvesting information from a particular application, we're not looking at the binary on the disk, right? We're looking at it at runtime because we don't care about it on disk. We want to know this operating system right now, what is it loading into memory and setting as executable? That's the most important thing that you can determine because it's not what you think, right? Instead of just executable data, it's also a lot of metadata to do with that particular application. It's the ELF header, it's strings, it's symbols. All that stuff gets loaded into the executable region and presented to you as an executable page. So you have to scan every single aligned potential instruction address for interesting gadgets. So we do just that. And that gave me an idea. And I thought to myself, it's really weird to think that we can look at metadata and actually have ROP gadgets that we can abuse at those locations. What if we didn't just look at executable data? What if we looked at persistent data, persistent metadata, or other interesting things like that? So if an application is running, what you can do is scan every single memory region that's loaded into the system at the time, and then identify gadgets in each one of those systems. And all you have to do is save the permissions of that particular page or set of pages. The reason why that's important is because, say you have an ASCII file, right, like a configuration file. It's loaded into memory. It's memory mapped or read or whatever. It gets into memory somehow. It's not currently an executable page. But on CISC architectures, where ASCII functionality can often be turned into opcodes, there may be useful gadgets in there. There's absolutely no reason why we shouldn't be scanning those regions of memory for instructions as well. So we do. And it turns out that it's extremely useful. When you're able to very easily set a page of one of these regions to executable, then you can start implementing your own functionality using these regions of memory without having to inject payloads. And I'll talk about that in a little bit more depth. So essentially what we do is save the data the way that any of you would. I'm not going to talk too much about it because it's boring. So we adjust for each opcode architecture. So the cool thing about our Inspector Gadget theory is that it's pluggable, right? So we have DieStorm 3 for x86 and x86-64, which I'm sure a lot of you are using. But why use anything else? Because it's awesome, right? And I'm not going to write my own CISC decoder because that stuff is insane. So instead, we decided there aren't really great instruction sets for, Spark, PA-RISC, PowerPC, ARM. So we decided to write our own DieStorm 3 alike libraries for those. I'll talk about that theory a little bit more later because it's not as simple as just writing a decoder. But it's important to note that essentially it is just a pluggable system for opcode architectures. So you have a distributed system. Let me increase that a little bit. You've got a distributed networked environment where you have opcode independent payloads or architecture independent payloads. And you can analyze them based on their metadata. So this is a little bit better to see, but this gives you an idea of what we're doing. We're taking all the information in the database, or storing the information in the database as gadgets with a lot of metadata attributed to it. And then we just pull that information out and say, hey, what gadgets are in, say, Whoopsie, right? And then it shows what they are, except there's really some interesting stuff that we can do because everything gets stored as two things. Instead of being stored as binary or being stored as text, we store both. So it makes it a lot easier for us to comb through information because now we can just search using regular expressions and then dump the binary from different perspectives. And that, of course, is important because misaligned opcodes on almost any architecture, well, maybe not some RISC, but it's important on Thumb, it's important on x86, that will actually result in different instructions being decoded, right, based on the alignment of the data. If you're on an ARM system and you have a 32-bit instruction and it's supposed to be 32-bit, if you jump into a 16-bit instruction and decode it as Thumb, it may be a completely different instruction that's useful to you. So it's important to get every single alignment, and we do that, and we dump each alignment independently so you can see how things change over time. So this is another good example of just doing a simple search for important gadgets. And this is essentially just displaying those different offsets and instructions. So we can actually see that these particular gadgets, this is actually all the same gadget, just decoded one different offset from each other. And you can see how things change. Things get more interesting as you go lower and lower and lower, but we'll decide whether or not these are valid instructions based on the metadata, because we can say, hey, this first instruction in the very last gadget we see on the screen, it touches memory. I don't like that this gadget touches memory, so you can discard it. So you can do classification on these kinds of things. That makes it nicer to use. So this is just another simple way of finding like a really nice gadget for stack pivoting, right? Just a leave and an add, except in this particular case, you're also going to want to watch out for memory dereferences as well. And this is just a lame display of how we actually have the process of building up the library. Because itself is interested in, like, Inspector Gadget is interested in the architecture, but it's also interested in all the libraries. So as I said before, it maps every single memory region into the running system. And it pulls each individual memory out, each individual region of memory out. And that's really important because the libraries that you presume are going to be loaded into a target application, especially if it's proprietary, are not necessarily what you're going to see running in the application later. And that's because some of these libraries and some of these applications do specific things where they DL open a specific library and then load that into memory. You may not see that through LDD, right? So it's really important to capture all of these things during the middle of execution so that you can take a snapshot at the point you want. So another piece of functionality that's really important here is that we can set a breakpoint and set scripts that allow you to say, this is what I want to do to a particular application, how I want the application flow to work, and then break on one final instruction, and that's when I'm going to harvest memory. So you can actually simulate some user behavior as long as user interaction, like a GUI, isn't required. So the thing that was most important to us when developing this application was the distributed nature of it, because it turns out that priming a system is extremely hard. And it's hard because dredging a system requires looking at every single library and application on the system, and that takes a long period of time. And there are certain aspects of that that are really difficult to manage, right? One of those things is if the target system is really slow, as in, we do a lot of embedded work. So if we're working with an embedded ARM board, that ARM board may be really, really slow. That ARM board is not capable of running our libraries, right? We don't want to decode instructions on a system where it has a small amount of RAM and a slow CPU. So we made it distributed. So essentially what we did was we created peers. We have a peering list. So now you can take Inspector Gadget, the client, and put it on as many different systems as you want. And all of those systems now have an application on that will talk to a centralized database. And the database will say, hey, I need information from architecture X, platform Y. And then one of the Gadget's clients will say, hey, I'm of that platform. And you can see it here. They know what platform they are. Ubuntu, Linux, 1304, x86, 64. And they can say, hey, either I'm busy, I'm already doing work, or I'm idle, give me work to do. So you just say, I need this application from this platform. It goes in the database, and all clients that are live say, oh, I'm capable of ingesting that. And they go and perform the work and ship the information back. So this is much, much cooler when you look at it from a large platform perspective, because it gives you the idea of taking every single file in the system, even stuff that you would never really think of ingesting. Like I said earlier, files is really important as well. So we have binaries, we have the ELF entry point, we have libraries, and we also, like I said earlier, databases and text files. That's all really important stuff to ingest. But again, all of these systems, unless a target application is Pi, you can just set whatever offset that you want, or you can just get it from the ELF endpoint or the ELF header for the entry point to the application, and then you can just run automatically without any user interaction. Where you do have Pi, there has to be a little bit more user interaction to actually determine what address you should be breaking on. So unfortunately, there's not full automation at that point yet, but everything that's not Pi can be loaded automatically. So the ingestion process is architecture independent in that it allows you to do whatever you want regardless of the architecture, because all the information gets populated into the database and then attributed a platform, right? But what's cool about that is you have the ability to read all this information as metadata based on the new decompiler architecture that we have. So the metadata that's stored isn't just about what instructions and where they are in memory, but it's also the opcodes themselves and the metadata that I'll talk about in a minute. So there were some very weird unintentional features here. And I think this is actually pretty cool, because I haven't seen anybody do this before. And we have the general problem that most people have with versioning systems. Ubuntu is a real pain in the butt with this, right? Because Ubuntu, or any other system like Ubuntu, will do automatic binary updates. And you don't actually have a minor revision to say, I am on this revision, right? I know what this application should be. So now, in our ingestion, all we have to do is just use hashes of a particular memory region, and we can automatically determine whether or not the system has changed. So we can actually watch opcodes change over time. And it allowed us to do differentials on versions in really interesting ways. We can detect gadgets that are deleted from the system. So in this instance, you can actually see, like, if you have developed an exploit that's using a particular set of ROP gadgets, you can tell if there's a change to the system that the instructions have now been removed. And your opcodes are no longer going to be useful, and you have to readjust your ROP chain to orient towards that those changes. And here, we've just got a differential of changes that have occurred in the system over time. So this is one snapshot versus another snapshot of these two different applications, and you can see how these gadgets have changed. On the left-hand side, you've got 06000, on the other side, you've got 0600C40, right? So you can see these simple changes and understand whether or not these are actually going to cause a crash in your gadget chain or not. So, to recap a little bit, binaries can essentially be analyzed at one of 2 points, right? This is pretty basic stuff. But this is also to ensure that any on-demand libraries are loaded, so you have everything that you know the application should be running at that point in memory. It also allows the system to use normal library load functionality, so you're guaranteeing that the information is going to be correct based on the kernel's point of view of your application, not your presumed point of view of how the application should be put into memory, which is a very important distinction, especially on certain ARM architectures. Also, for libraries, it's really not that interesting, but just to let you know, we're using a stub. So if I want to target a library, we just have a simple loader that then uses that particular library, links to it. Now you have an application that loads that into memory. Text files that you want to dredge on the system are also memory mapped. So that way, all the gadgets can be accounted for. Now, statistics here are really important because it's extremely slow, right? Like this is the slowest thing that you can possibly do is dredge a system on a slow CPU. The original version of Inspector Gadget Alpha was dead slow. This was going to ingest one binary. Of course, it was Chromium, but at the same time, it was going to take a week to ingest this. Then, of course, the beta was moving to MySQL. And by moving to MySQL and implementing threading, we just cut it down to about 2 days. And now, because Gamma has a distributed architecture where we have client nodes on different systems that can all be populating the same exact image at the same time using threads and a distributed MySQL database, now it runs in hours. So we have a significant significant achievement of functionality over time in ingestion. And the queries themselves are just blazing fast because we no longer have to care about the binary data or decode it unless we really want to do that. Since everything is essentially text, we can just create regular expressions and bam, immediately you have your result. So practical use, of course, of these gadgets is essentially rebasing. So the exploit example that I showed earlier has a module, okay, where Inspector Gadget says, I'm going to rebase the information that's pulled back from Firefox, right? So Firefox has a memory leak. We harvest the memory leak and pipe it into Inspector Gadget. It says, I need to rebase my ASLR environment based on these gadgets, on the information that's been given to me. So it readjusts the alignment, base address plus offset of whatever is stored in the database based on the ROP chain that are predefined to use. And then it generates the payload and ships it back, and that's what's used. All right? Now, that's done using a preset ROP gadget chain that can either be generated automatically or can be generated by the user. The other interesting thing is that it can also create binary monitoring, right? The manual searches stuff I kind of just told you, but the binary stuff, the monitoring is really interesting because if you have differentials, you know based on the information that's provided from a memory leak. So if you don't have a version information of the target, the information leak should be slightly different depending on the exploit and give you enough information to almost have a version fingerprint to allow you to then generate your own gadgets based on the version that's identified from the memory leak. So monitoring a remote binary is possible as well. In practical use, this is where things got really interesting. Kind of running out of time. The impractical use is really path traversal, right? Because this is essentially automated gadget generation, right? So I'm going to kind of go through these slides very quickly because they're cool, but I want to get to the main points. So path traversal is really important because this is really where the application comes into play, the different features. And from the different features, I'm talking about Penny Gadget, Penny, Inspector Gadget, and Brain. So if you've ever seen the cartoon, there are 3 cartoon characters, and they each function in their own specific way. Inspector Gadget is basically an idiot that stumbles onto information that he really shouldn't have. So that's basically gathering metrics on gadgets. So if you're generating gadgets automatically, This guy is going to go harvest information about all the gadgets from the ingestion system and say, I think these gadgets are useful, but I have no idea whether that's true. Penny's functionality is to evaluate paths that are identified by Inspector Gadget, right? So Penny takes the information on like, oh, here are some good gadgets, and then I'm going to determine whether or not a path can be created. Brain's job is to run each path and determine whether or not that path is valid, right? So Inspector Gadget itself is completely metric oriented. And the reason why is because we don't necessarily know whether a gadget is good or bad, right? It's very complex to tell. There are too many ways of interpreting a gadget or too many ways of generating opcodes that don't really allow you to have a clear understanding of what the side effects are going to be of a particular gadget. So the idea here, Inspector Gadget just simply weights everything. And by weighting everything, he decides whether or not something can be useful for the particular target. So each gadget is analyzed by a variant of Inspector Gadget. So he's essentially a factory, right? And by a factory, I mean like he has a base class, and then each child class of himself has a reflector that will say, I can interpret gadgets in this fashion, right? Either I can find something that looks like a stack pivot, or I can find something that looks like mprotect, or I can find something that looks like XYZ, right? And it will reinterpret the data based on that information and say, according to my instantiation, I think this gadget has a weight of X and a value of Y. And those results chained together give you really powerful ways of analyzing gadgets in unexpected ways. So this is a really simple way of just taking simple dumps of gadgets, classifying them by weight and value, and then reassessing them for their use. Penny herself then identifies paths based on the weight information provided by Inspector Gadget. So her job is basically to ask her dad, Inspector Gadget, go get me information. I need to solve a problem. Here's the metadata about that problem, as in I need a stack pivot. So I'm going to instantiate the gadget classes that are oriented towards stack pivoting. And then Inspector Gadget will harvest the information, but he's going to come up with thousands of potential gadgets based on weight. And then Penny evaluates those thousands of gadgets to break down each gadget into the best classes. And then she'll say, okay, I think I have a path. Now, you're talking about potentially hundreds of thousands or more gadgets in a target application, okay? So things get extremely complex, but using a modified version of the Dijkstra algorithm, we can actually do this very quickly. So pathing only takes, like maybe a couple hours on a really complex system if you've ingested all the binaries already, right? So an interesting point about Dijkstra is that Dijkstra itself presumes context, right? So when you're walking a path, you usually know what's behind you, and you usually know what's in front of you. These are really important attributes of understanding, solving a vectoring problem, right? The issue with gadgets is that you don't necessarily know whether where you're going has completely changed. You're no longer walking forward. You're walking forward and then somebody's spinning you in a circle with your eyes closed and you have to guess which direction you're facing, right? So in this instance with gadgets, you have to reevaluate your world every single time that you take a step forward. And when you take a step forward, you actually may be taking 3 steps back without even knowing it. So the idea is that once you've accomplished the initial Dijkstra pathing algorithm and you've identified potential paths by Penny's functionality, you then hand that off to Brain. Penny doesn't actually understand whether or not an app can die, okay? So this is a really important theory in gadget hunting or automated gadget hunting, because you can never really know conclusively whether or not a gadget you're using is going to result in app death without running the gadget itself. So the result is that you have paths that are defined by a gadget hunting application like Penny, but you have no idea whether they're going to work solidly or not. They may work one time, they may not work 30 times later for some unknown reason. You don't know why, okay? And also this depends on the actual metadata or other raw data that's in memory at the time. Maybe the user browsed one website today that has HTML. Maybe the next time they're browsing a website that has SVG. Maybe the attributes in memory are causing things to change and causing a gadget to fail unexpectedly. So you don't know whether that's going to occur or not, and we have to accommodate for that as best as we can. So that's pretty much Brain's job. So essentially, when we look at the overall stack pivoting process, or I'm sorry, the exploit development process, you're looking at each step that needs to be solved independently with reference to app death. Okay, so now we don't know for every single instance of this flowchart, we don't know whether some app is generated app death or not. Brain then runs each path. And he can do that in two ways. And this is where things get really cool. Because Brain's functionality is to say, I have path X, Y, and Z, or many more. I need to determine whether app death is a potential. I need to determine whether or not these gadgets can even function or accomplish the goals that I think they can accomplish. You can do this in one of two ways. You can automate a GDB script that says, hey, I know what all these gadget addresses are. I know what the functionality should be. I create an automated set of gadgets using a GDB payload that steps, changes memory, steps, changes memory, steps, changes memory. And then the result is executing a predefined payload. And say the predefined payload touches a file in /temp/foo. If you run 10,000 different path variants and only one of them actually touches the file, you've still won. It's taken maybe a day to run all of them, maybe 2 days, maybe a week, who knows. It doesn't really matter. All that matters is that you can run them, and eventually something will succeed. So it's algorithmic based, but it's also heavily on brute forcing because there's no way for us to actually guarantee that these things are going to work correctly. So the result is basically fuzzing your own ROP compiler. But it works, and that's really cool. The other way that you can do this is through metadata in instructions, and that's where we're going with our ARM decompiler. So the ARM decompiler itself has metadata inside each instruction that's decoded, and we can use that information to go and run paths much faster. Because you can imagine GDB requires GDB to be on the system in the first place, which not all systems can. And if you're targeting some application that's on an ARM system, like say a little, I don't know, some kind of gadget or a phone that you don't really have the ability to put GDB on, then you're screwed, right? So there needs to be another way to do it. And the only way that you can do that is by having a decoder that also understands enough about the instruction to generate metadata that's going to be useful for something like a path running algorithm. Okay? So Brain also evaluates gadget noise. And this is great because the noise that's generated by a gadget is really easy to see. And you know it when you see it, right? And that's like, oh, this gadget touches memory, but in really weird ways. I, in my mind, classify that as high noise. So we can do that algorithmically by looking at the gadgets and saying like, oh man, there are a lot of instructions here that are touching memory. I don't want to analyze whether or not what it's touching is valid. All I want to say is it touches too much memory. I'm going to set a very high noise value and a very low value, right? As in like, this thing is not really great. I don't want to use this gadget because it doesn't seem to be functional. So it can test paths with less noise. So each gadget that you see, it can attribute the metadata to it, and the result is essentially going to be, I know these gadgets are high value, I know these gadgets are high noise. I'm going to deprecate the ones that have high noise and use the ones with less. So Brain itself just evaluates paths on, based on noise, essentially, and then brute forcing everything to determine whether or not it can touch a file. But it works and it's great. And together, Penny and Brain themselves are actually a really powerful process. They allow gadget hunting and gadget path development in a reasonable amount of time. I'd like to do this a lot faster, so we're thinking about ways to do it faster, but right now, it depends on the complexity of the target environment. So this is another way that things get really interesting, and I'll try to go quickly with this. This is MOP. So people talk a lot about ROP, and then people want to talk about JOP. People want to talk about whatever else to do with gadget hunting. To me, it's all just return to libc, right? Just with a cutesy name. So I invented a technique called MOP, which probably isn't really a technique that I invented, but I'm going to say that anyway because MOP's a fun word and I want to attribute it to my name. So MOP is basically analyzing memory for instructions that are already there. And not instructions that are already there, but pointers that are already there to gadgets that are useful, right? So the idea behind this is we have an ingester system, and this is just a web-based ingester for visualization that I've designed. So all we have to do is say like, oh, I want to ingest bin Python. So right now, I'm actually going to automate the run process of bin Python. So I'll execute it. It'll be slow for a second, and it'll come back and give me an increased PLID. So I know now that it's ingested the Python application just as I would in a normal inspector gadget run. So then I just say, oh, all right, well, let's visualize run 31. And there you go. So what you're looking at is the Python application. But every single attribute here, if it's green, that means it's a writable region of memory. If it's red, that means that it's an executable region of memory. And if it's black, that means that it's a read-only region of memory. So we can see all the pieces of data that are relevant to this particular application at a particular point in time. Because again, this was given, the system was given the instruction to say, load this application into memory and harvest all the memory regions, but do it at a breakpoint. And the breakpoint is, in this case, because I didn't assign a specific one, but in this case it's, I'm going to give you a breakpoint of the ELF entry point. So at ELF entry point, when the application starts, when Python starts, all of these libraries and memory regions are loaded at that time. So what's cool is I can actually see it by tree. So if I look here, I can identify, oh, that's the actual Python application, right? And I can identify the other memory regions that are a dependency of that particular memory region. So I can see the read-write, I can see everything that's important to that. Now if I go and find stack, I can visualize the stack and determine what application or what objects are in stack at the time. So it'll run for a second, and then bam, there you go. So now we're visualizing all of the objects that are in memory right now. And in this case, I haven't given it a specific object to hunt. So what it's doing is visualizing all of the pointers that are in the stack region right now. So it goes through the entire region of stack and says, for every other region of memory that's in the application right now, libc, DL, Python application, whatever, show me all of the pointers on the stack that point into one of those memory regions and then map it. Okay? So here all I do is I look through and I say, oh, what's most interesting? Here's a really small thing. Here are all the pointers to instructions in libpthread. So these are basically return values into pthread somewhere, right? Because they're on the stack. So they're most likely to be return values. And this is, the largest blob is, of course, stack pointing into itself, as in, you know, other values saved, stack pointers saved during function execution and whatnot. If I look at some of the other things, I can say like, oh, this is libc, blah, blah, blah. But what's great is if I hover over these, it actually gives me the offset into this stack region and then the value at that particular point. So I can see like, oh, hey, I want to go analyze an executable binary, right? So this is an executable region, LD, right? And I want to look at an attribute, this value, which I don't know what the value is, but I'm interested in it, so I can click on it. And it'll actually go and automatically find the gadgets that are attributed to that memory region at that time. So what's really important about this is now what we can do is we can visualize it this way so that I can look at it manually and find what's interesting, or Inspector Gadget can hunt through memory, look for these pointers, and say these gadgets are useful as well. Because now I don't just have to inject ROP payloads into my target application. I can use existing payloads that are already in memory, which decreases the amount of metadata for my exploit that I need to ship over the network. So basically now all I have to do is send over the network an offset, and that's it. No instruction pointers, no stack pointers, just an offset. And the offset allows me to reach into that memory and say, my next gadget is here. That address is already a pointer in the stack. And now my next gadget is going to be that pointer in the stack in the next runtime, which means that it's extremely hard to decode and reverse engineer. IDS is never going to find this, right? Because it's just looking at opaque offsets that mean absolutely nothing. If they saw addresses that were relevant to a particular application or region of memory of application memory that would be used at runtime, it would say, hey, I'm going to flag this. This looks dangerous, right? And that's presuming you don't have encoding and all the other stuff, but bear with me for a second here. So the opcode itself doesn't need to be placed. All you have to do is use that alignment, and it also makes payloads much smaller. Because opcode alignment doesn't have to be 64-bit, but an address does. But now you may only need 16 bits in order to get to a ROP gadget that you actually care about. That's a significant win. The other thing you can do is look at regions of memory that are writable. And you can actually dump memory at those points. I guess I should actually just look at stacks since I want something writable. And this isn't great. I need to improve this, but it'll dump the hex dump around that particular application or around that particular pointer in memory. So when I actually care about this functionality more, I'll make it prettier. But right now, it's not all that useful to me. But the primary thing is the concept of MOP, or memory-oriented programming, where now it's much, much easier for you to scan existing regions of stack or some kind of writable memory for things that are useful to you and then pointing into that attributed memory, right? Because you have a guarantee that they're going to function. And what's great about this system is that you can watch runs occur over time. So if you have a target application like Python and you run it 300 times, it will visualize the changes in runs to say like, oh, run 1 through run 20 all had the exact same stack layout and all the exact same variables in the stack layout. And you'll see a decreasing amount of those attributes in the actual starburst graph that you saw. It'll start showing you less and less values. As more values are stable, it'll show you more data. As less values are stable, it'll show you less data. Here are the points that are stable over 300 runs or whatever. That way you know this is the most likely thing that I can use to have a stable environment if I want to use MOP in my opcodes. So that was the demo. The objective assembly point is just that we're now using metadata to analyze run information. So we can say, oh, we've got an ARM library, and it has instructions that decode as objects. So instead of just getting text from a particular opcode, you now get an object that says, yeah, I've got the decoded information, but I also am an object that contains all the metadata about this information. And if you execute my functions, I will analyze the instruction and give you attributes, whether it's memory or whether it's arithmetic or whether it's whatever, and tell you the noise, the classification, etc. That gives you a much easier time to make runs with Brain to determine which paths are going to be correct. And it gives you a much easier way to say, I have a guaranteed high noise value on these particular instructions. They're no longer relevant to me. Okay. So I'm running out of time, so I'll just go ahead and blast through the front end stuff. The visualization stuff is really useful for manual work, but that's really the only visualization that we have right now. Everything else is command line. Because it's the only thing that we've been working on is, we're command line guys, so we don't really care about anything else. So the idea is that we need to link this all together in an efficient way to make it useful for other people. But the whole goal is achieved. We've got a volatile, vulnerable environment that we've induced using an exploit, and we are changing that volatile environment to a stable environment using pathfinding, using Brain, Penny, and Expector Gadget. And it allows us to take an extremely volatile system and define a platform upon which we can now execute any payload that we want to in a predefined way. Which is the most important thing with exploit development, is in issuing a premium platform for executing any arbitrary code you want. Right? So if you want a web demo of all this stuff and you're interested in this technology and how it relates to you and your processes, then hit me up and we'll give you a web demo. We're in the process of getting our patent, so it's going to be, I don't know, a month or so before we're actually going to do licensing. But it's cool stuff, and if you're interested in it, give me a shout, and we'll see what we can do with the demo. So I'd just like to thank my business partner, Matt Skinner, who is a brilliant mathematician, and without him, I would not have been able to write this because I'm horrible at math, Don't ask me to add two numbers together. My wife for dealing with my bullshit, mainly. And also JDuck, who reminded me that I forgot how certain architectures work, primarily ARM. So that's pretty much it. The goal is that you go from a vulnerable state, a volatile state, to a platform. But at the end of the day, all you want to do is kick back and get the beer. That's exactly what this application does for you. Less work, less exploitation bullshit, more beer. All right? Thanks.